Hi all, welcome back. Today we're going to continue our module on thermodynamics, and we're going to explore what exactly is a system that we talk about when we're talking about a thermodynamic system. By the end of this video, students will be able to describe what makes a well-delineated system and delineate their own examples of a thermodynamic system and identify whether it exchanges matter and heat with its surroundings. So, you're certainly familiar with the word system in common parlance. For instance, you've heard of the circulatory system that moves blood around our bodies. You heard of an electrical system that powers your home. You've certainly heard of an ecosystem, being environmental scientists, which is a system that organisms inhabit. And you've all heard of the global financial system, which governs how money is moved around in the global economy. All four of these things are very disparate objects, though. There's seemingly nothing that unifies these things into a coherent thing that can be described as a system. So why are all these things called systems? Is it just a quirk of different language usage in different disciplines, or is there actually a unifying principle that allows these all to be called the same? So the answer to this question is yes. There is a coherent definition of a system that allows us to include all these seemingly disparate examples within the same definition of a system. But you can only arrive at that definition if you consider a system not as something actual that exists in the world, but instead as a human construct, as a tool that allows us to interrogate what's happening in an object of interest. And that tool is simply to draw a boundary around something and say that everything within that boundary is part of the system, and everything outside of that boundary is not part of the system, it's part of the surroundings. And hopefully by drawing this boundary, it allows us to narrow our focus to interrogate the internal changes within a system that change its properties, as well as the movement of materials and energy across the boundary that allows us to describe how the surroundings are affecting the internal state of the system. So just to stick this in a bit more formal language as a definition that you can stick in your pocket, a system is a tool made by drawing boundaries around objects of interest, such that the internal properties of the system and exchanges of materials across the boundaries are well defined and hopefully quantifiable. So let's look at some of our examples from previous. Considering the example of the ecosystem that we have a lake shown here. And the lake, it's pretty easy to draw a boundary around. You can put a boundary around the shoreline, as shown here. And you can also quantify the fluxes of materials into and out of the system. Say that the materials of interest to us are fish. We can quantify fish coming in via the river shown at the top of this picture of the lake. And we can quantify fish coming out by measuring fishermen's catches. And so we have a well-defined system that's outlined by the lake, a shoreline, and we have well-defined fluxes that come in and out. So this makes it a pretty good, well-defined system. There's no way that fishes are going to leave via any other method in case some birds catch some fish, for example. Or consider the circulatory system example that we also considered. We have pretty well-defined boundaries. Our circulatory system consists of our veins. It's basically anywhere that blood can go. And if our material of interest is oxygen, we have a boundary in the lungs where the blood vessels interface with the lung tissue, where oxygen can come in, and we have places where oxygen leaves the system, the capillaries, which supply oxygen to our organs, such as our brain. So like the ecosystem example, our circulatory system is an example of a pretty well-defined system with well-defined boundaries. Namely, anywhere that blood can go in your body is part of the circulatory system. Anywhere blood cannot go in your body is not part of the circulatory system. So I've said what we mean when we talk about a system in general, but now let's drill down and talk about what we mean specifically when we talk about a thermodynamic system. A thermodynamic system is a pretty exhaustive definition of a system in that it's a system with boundaries such that the exchanges of all forms of energy and matter between the system and its surroundings are well defined. So you have to be able to count for basically anything that's coming into and out of a system. So it's, like I said, a fairly exhaustive definition. When discussing the properties of thermodynamic systems, we make distinctions between systems based on the permeability of the boundaries of the system to both energy and matter. We'll consider these different types of systems in turn now. For example, An open system is a system where the boundary is permeable both to matter and to energy. So the lake example that we just brought up, if we consider that as a thermodynamic system, is a good example of an open system. Matter can come into the system, water can flow into the system, fish can flow into the system via the river, fish can leave the system via fisherin, and energy can enter the system as well via sunlight shining on the lake. Contrast this with a closed system where the boundaries of the system are impermeable to matter, but they aren't permeable to energy. So energy can come in and out of the system, but all the matter that's in the system stays put. And these systems, true closed systems, are rare in environmental examples. But we'll see in a second how we can actually treat some open systems as a closed system and why that's a useful thing to do. Thirdly is an adiabatic system in which neither energy nor matter can cross the boundary, but the boundaries are flexible and the exterior of that boundary can push against things in the surroundings and do work on the environment. We often talk about air parcels moving up and down in the atmosphere as being adiabatic systems, but we won't really touch on this much further. Finally, we have an isolated system, which is purely a theoretical construct. An isolated system is a system that neither energy nor matter can transgress the boundary of, and these don't actually exist in the universe, but certain physicists use them as convenient shorthands for solving otherwise hard problems that are hard to consider as an open or closed system. Okay, now let's consider some real-world examples of systems. First, let's start with a closed system. A closed system, you recall, allows energy to traverse the boundaries, but not matter. And I think a good real-world example of this is perhaps a pressure cooker. You know, with a pressure cooker, you put your food and your water in the pot, you close the lid, and that food and water can't escape from that pot. But energy can traverse the boundary of that pot. You put the pot on your stove, heat comes in through the bottom, and it heats the food inside the system, and it does work on it. It cooks your food for you. So this is a good real-world example of a system that can be considered a closed thermodynamic system. Now consider by contrast open systems. Open systems, you'll recall, allow both matter and energy to traverse the boundary of the system. And I think you'll find that most real-world examples of systems are indeed open systems. There are very few closed systems in the environment. Some examples of this, we've already talked about how a lake can be considered an open system. Energy can come in through sunlight, can leave through heat. Matter can come in through stream flow and it can leave through evaporation. Another good example of an open system that's relevant for this class is a groundwater aquifer. Water can come in through rainfall, enter the aquifer, bringing along heat with it, and water can leave the aquifer via flow into a river. A river is another great example of an open system. If you draw a box around any section of a river and say, this is my system and everything that's outside of this box is my surroundings, then obviously in this river you always have matter flowing in through the flow of the river, and you always have matter flowing out of that box. So a river is another good example of an open system in thermodynamics. But you recall that the study of thermodynamics is the study of equilibria, or the study of states that are at rest, where systems are not changing at all. So if you constantly have matter moving in and out of a system and energy moving in and out of a system, how can we talk about the thermodynamics of a system? How can we talk about thermodynamics of an open system when that system is indeed never at rest, never at equilibrium? And on one hand, it doesn't really make a lot of sense, but we can do it by making sort of an approximation. And that approximation is made by not considering a closed system and an open system as a dichotomy, but kind of considering them as a gradient between each other. And some systems, for the purposes of thermodynamic calculations, can be considered as what I would say is an approximately closed system. So if we consider this lake example again, yes, there is a river flowing into the lake, but that lake is huge and that river is tiny. And so the amount of water entering the system at any given time and the amount of water leaving the system through evaporation, for example, is relatively small relative to the volume of the lake. So although there are minor changes occurring at the boundaries of the system, we can kind of say that those changes are essentially a rounding error in our thermodynamic calculations, and that for all intents and purposes, the lake can be considered as an approximately closed system for the purposes of doing thermodynamic calculations. A groundwater aquifer can be treated similarly. You know, a groundwater aquifer might have a few millimeters of rainfall enter it every year, but the water that's in that aquifer has been accumulating for tens and thousands of years, maybe hundreds of thousands of years. And so the amount of matter entering and leaving the boundaries of that system is relatively small compared to the total volume of the system. So again, a groundwater aquifer can potentially be considered as an approximately closed system. This will, of course, depend on the properties of the aquifer. It can't be a blanket statement that the aquifer can be considered as an approximately closed system. But this won't always hold. So for example, a river, except over very, very short timescales, is probably going to be still described as an open system because the volume of that river is small and the amount of material crossing the boundaries of whatever box you draw around that river to make a system is going to be very large. It's going to be dominated by flow into and out of the system. So unless you're talking about reactions that happen over very, very short timescales, a river is probably going to remain best described as an open system. But this concept of the approximately closed system is a very powerful concept because it allows us to make assumptions about the state of the system that allow us to do thermodynamic calculations and determine what state the system is evolving towards if it won't eventually reach it, although it might potentially reach it. That's not to say that studying equilibria in an open system is a pointless activity. In fact, it's very useful. By studying equilibria, we can determine what reactions are possible in this system, so which way reactions are going to be heading, even despite the constant input and output of matter in an open system. You can always say what reactions are possible versus impossible. Now, it might be that these reactions are happening slow enough that you never reach the equilibrium condition in an open system, but it still tells you that the reverse reaction is definitely not going to be occurring in this system. So open and closed systems both have applications in thermodynamics. So thank you. That's all I have for this description of what a system is. In the next videos, we're going to dive into the laws of thermodynamics and figure out how these laws of thermodynamics drive chemical equilibria in the environment. So thanks for listening.